started. I don't remember. But
No, I mean, it was like, one solution is this.
I should.
Okay,
I think it's that. So I saw it.
So the last thing I'll let you with is this definition of what we call an integral domain. Sometimes I'll be very lazy and just call this domain. But it is a commutative ring with identity. Has to have identity. That's a part of the definition. If it's only zero divisor, it's zero itself. And so this is what the important thing about an integral domain is, if you have A times B, where A and B are elements of the domain, if the product is zero, that means one of them is zero. And this is something that you've used in math classes forever and ever. So for example, suppose we have so this might have been a problem if you had high school. Find the roots of this polynomial. Anybody?
I believe I know. X minus 7, X minus 5.
Okay, so that will be the first thing you do if you're looking for roots in the old days, is you try to factor this one. And this one factors in a convenient way. Now, if you set this equal to zero, if this is equal to zero, then this implies that x equals 7 or x equals 5. And really what you're hinging this on is the product of these two things is zero. That means one of these two things has to be zero. So either x is 7 or x is 5, right? Everybody, okay, so this is why integral domains are important. So for example, let me see if I can get you a example. But this is an example, so it's not a domain. So if you're doing polynomial factorization and your roots can be taken from C6, you better be a little bit more careful. Let me give you another example as well. If you look at this ring right here, this is just the even integers. This is a ring, right? Sums, sides, even integers, even, etc. A times B equals 0 implies A equals 0 for B. That is, this ring has no non-zero zero values, right? You can't multiply two things that are non-zero, right? In fact, this is a subring of the integer. Right up here with that. This is not a domain. Can you tell me why? Why is this? I mean, it's got no non-zero zero values. Why is it not an integral domain by definition? There's no identity. There's no identity. So that is actually an integral part of this definition. Part of the fun. Okay, any questions?
Just C6 is not one that's, there's not zero.
Right, I mean, yes, C6 certainly has an identity. One bar is an identity, right? But it's got non-zero zero values. Okay, proposition. So this is probably not gonna shock you, but prove it anyway. Proposition, any field is movable. So any field is automatically, in fact, right. Um, Okay, suppose I have a field, and suppose that I have a zero divisor A. What does it mean to be a zero divisor? So let's get down to the nitty gritty of that. That's right. There's a B such that A doesn't equal zero, but I've got to ask you for something else. Something very important about that B. That is correct. There's a non-zero B, but when you hit A with it, it's zero, right? That's the important thing. Now, what do we know about a ring? It's a field. What is true about every non-zero element of a field? Right. Since B is not zero and R is B. B inverse is in R. Right? Now multiply both sides of this equation by B inverse. And I get A is equal to zero. And so what we proved here is the only zero divisor is zero. And so that establishes the result. Okay. Any questions? Here's, and in fact, I kind of alluded to this, that example that I did factoring polynomials earlier. Suppose R is a ring with no non-zero, zero. That is to say, the only zero divisor is zero. If A, B, C are in R and AB equals AC, then it's not correct, but that's the thing. If A, B, C are in R and A is not zero, then when you see an equation like that, what you're hoping you can do? Both I can cancel. And in fact, this theorem is called cancellation. Integral domains have cancellation, cancel non-zero elements. And in fact, this is a more general statement. You don't really need integral domain, you just need no non-zero zero divisors. You get cancellation. notice there's no hope of cancellation if A is zero, because I can have B and C be anything, you can multiply by zero and get equality, right? But if A is not zero, then I'm good to go. Proof is not difficult at all. This implies A, B minus A, C is zero. And this is a ring, so we've got the distribution property. Now, what do I have here? I have a product of two things. One of them is called A and the other one is called B minus C, and their product is zero. So since R has no non-zero zero positives, and A is not equal to zero, what can we conclude? This product is zero, and this guy is not zero. And since there's no non-zero zero divisors, that forces this person to be zero. And if B minus C is zero, then any questions on that? This is kind of a cool theorem I'm fixing to get you, and we're gonna use it to, get a very kind of famous result in basic ring theory. I gave you, an example last time. Do you remember this example? And we concluded, I believe, in this example, that every element was either a zero divisor, which was in the case when the determinant was zero, or a unit in the case when the determinant was not zero. If you change the example to this, this is no longer true because, by the way, so if you have a 2x2, you have a 2x2 matrix. So this is just intuitive. We're not going to prove this yet, but I won't have to see what y'all think. So in this ring here, A, B, C, D are far restricted from the previous. Not just any real, they've got to be in. Let me ask you this, what can you say about the determinant of any matrix like that? It's also an integer. Everybody agree with that? Does anybody want to guess a condition that we need for an element to be invertible in this ring? The determinant has to be plus or minus one for it to be invertible. It turns out, right? Because basically here, the determinant can be anything in R, agree? And as long as it's not zero, you're good to go, because R is a field. However, here the determinant can be any integer. If it's zero, it's not invertible, no doubt about that, right? But even if it's something like 2, it's still not invertible. It would be invertible here, but basically you don't have that one half to help. Now that's very fast to listen to and see if you can prove that. But the units of this, so the zero divisors of this will be all the matrices that have determinant 0. The ones that have determinant plus or minus 1 will be invertible. And the ones that have determinant that are not 0 or plus or minus 1 will be what we call regular elements. Neither a unit nor a zero divisor. Like 2 is in the integer forms. Here's my theorem. So the moral is, in most rings, if I walk up to you on the street and give you a random ring, you can expect it's probably got some zero divisors. Probably. If it's a ring with identity, it has to have at least one unit, namely 1. And it's probably full of what we call regular elements that are neither zero times nor problem. Right? However, this is a rather striking example here. Theorem 9-1. But R be a finite commutative ring. Actually, now that I think about it, yeah, it has to be. Let's look at proof. I think we might be able to scratch up commutative. At least you don't need commutative for at least some of this. We'll see how the proof goes. That's the great thing about that. Let's see how the proof goes and see if we can shake this down a little bit. Well, for sure, if R is a finite commutative ring, then any element of R is a unit or a zero. And let me, just so that we don't get into silly logical arguments, let me assume that R is a non-zero ring. So it is a ring that consists of at least one thing that is not the freaking zero element, right? So if you've got a finite ring, I put in the hypothesis commutative, then any element is a unit or a zero divisor. Anybody's spidey sense going off? Oh, maybe yours. What?
I was just gonna ask, can you make it even stronger with built in? As opposed to zero?
That's not true. That statement's not true. But is there something that might look like it's missing from this? I didn't say it has an identity, right?
It doesn't have to have an identity.
Actually, it doesn't. The identity is forced. If there's one element that's not a zero divisor, you have to have an identity. And you'll see that.
Oh, now this makes homework a lot easier, like optional problems.
So let's pick. Well, actually, let me go further. Put A and R. The not, I'll count this way, even though it sounds clumsy, it might be more clear. Let A and R be not a zero divisor. I claim that A is a unit. Now, this is a wild claim to make at this juncture because I haven't even said that the ring has an identity, right? Look at me spouting off like this, claiming it's a unit. I don't even know if the ring has an identity. We will prove that along the way. So what do we know? I know that A is not a zero. That's it. I don't even know if I have an identity. How am I going to prove it's a unit? Let me look at follow step. Look at the set powers of A. What do we know about this set of powers of A? Let's see, my notation. What do we do about them?
It must be finite.
Okay, this is a subset of R. And I know that R is finite. Now, this right here, if you consider it as a list, it's certainly an infinite list. But this infinite list denotes a finite subset of R, right? So what must we conclude? There has to be repetition, right? So there exists integers. Infinite list is finite set. So there exists well, actually, I'm gonna say neutral numbers here. And I'm gonna take m to be bigger than 1. Such that so in other words, you have to hit some point, a to the m, where you can repeat later at a to the n. Right? Because otherwise, if there's no repetitions, then that has to form a set, right? Am I okay with that? You might be a little, how do I know that I can pick n bigger than 1? Well, if it's not, then I can just multiply both sides of this equation by a, and then I get a to the n plus 1 equals a to the n plus 1. So I could have assumed that n is bigger. Right? Because once this equation holds, it holds for any multiple of n that you, or not multiple, any power of n that you multiply on both sides. Right? Okay. Okay, and we'll see why I wanted n to be bigger than 1 in a moment. So this means that n minus a to the m equals 0. And I am going to pull out an a to the n minus 1. Everybody okay with that? This is why I wanted n to be bigger than 1, because there's no guarantee that I have a to the 0 power. Right? Because remember, I'm not assuming that there's an identity. So I want to be careful with that. Everybody okay with that? What do we know? A is not a 0 divisor. So neither is a to the n minus 1. See if you can show this by induction. It's not very difficult to show by induction that a is not a 0 divisor, then no power of it. Everybody comfortable with that though? So if this is not a 0 divisor and this product is 0, what must be true of this animal? That means that other factor has to be 0. If this is not a 0 divisor and their product is 0, this has to be 0. Okay, so far. So I'm going to use this equation, that is, or I'm going to use it and this a to the n minus n plus 1 equal to a. Now I'm going to make this wild claim here. I claim that I now make the following. I claim A to the n minus m is the identity bar. Right? Notice A to the n minus m makes sense because n is bigger than m, and in fact, n minus m is bigger than one, so that's at least the first value. How are we gonna show this? Well, let's suppose that, let B be any element of R you want. Notice that, B everybody agree with that? How did I get this? I got this by multiplying both sides of this level. Everybody agree with that? Now I'm gonna do a little bit more doctoring with this. This is an A times everybody agree with it? Yes,
Is that required?
what's it?
Is that required? Commutativity?
It's what?
That requires commutativity, you were saying?
Yes, yes, yes. Actually, you're right, it does. But I think that we probably could wiggle around it, but here's the point. Actually, I'll be a little bit more explicit in this. Rearranging this equation to that. But A is not a zero divisor. And so. This piece has to be zero. Agreed? Therefore. We're all being on. So there it is. So A to the n minus n is the identity element, because when I multiply it by any element R, it leaves it alone, right? And the identity is unique. Notice this would work for any element that is not a zero divisor. There is a power of it that is the identity. That's something we can glean from this. So what this says is, well, actually, sort of a corollary to what we've done so far is if you have some element that's not a zero divisor, a power of it will get you the identity. And so this concludes the proof because since A, the n minus m is the identity of R, A is a unit. And there you go. Power of A is the identity. That means that A has an inverse. Namely, it's the one less power is the inverse of A. Okay. Any questions on this? Yes.
The identity is always.
Yes, the identity, if a ring has an identity, that sucker's always a unit because it is its own inverse. Here is the famous corollary to this that I promised. That's kind of cool though, that in any finite ring, everything is either a zero divisor or it's unit. Corollary 9.15. Any finite integral domain is a blank.
Division ring?
You are technically correct, but there's better terminology for dealing with community brain.
Deal?
Let me know. This is very famous. If you have a finite interval domain, it has to be deep. And this depends on the previous theorem in a nice way. But by assumption, X is not a zero divisor. Because that's assumed in corollary. And since R is finite, nine point one point fourteen is that X is. So what we've shown is any non-zero element is a unit. So R is a field. If any non-zero element has to be. Okay. Any questions on that? So I'm going to get into a couple of things, and I'll point out that there's some kind of arguments in the terminology in the literature. I'm going to find a general subring. So let R be a ring. A subring of R is a subgroup of the additive group of R. Subgroup P and R. So here T is just some subgroup of the ring as a group that is closed under multiple. That is to say X, Y, and P implies X, Y.
Same multiplication,
What's that?
back to the same multiplication.
Yes, yeah, that's right. It's the same multiplication operation that you're inheriting from R. It has to be close. Yes,
So it's a subgroup, like respect to R plus, like R with the addition. of
yes. So any subgroup that also has a special property that's closed under multiplication from R. So if you have two elements in the subgroup, their product is also still in, right? So basically, it's exactly what you would think. What it is it's a little baby ring inside the big ring. That's all it is. Sometimes it is demanded for subring that if R has say one R, then one R is. Some authors use this when they're talking about exploring subrings. So some authors would say that the even integers is not a subring of the integers. Because you don't have the identity in it, right? Some authors demand that the subring shares the identity. For our purposes that's like more sophisticated later. For our purposes right now, subring will take the broader view of any, just what I said in the definition, any subgroup that's also closed. I'm not going to demand that an identity be that there, at least not yet.
Yeah. but What would be the usefulness of defining it the other way? Like, is there some certain properties that get out of the?
There's actually kind of categorical properties that are important. There's some other things about, for example, if you look, so sometimes I study subrings as well. And when I happen to be doing research on factorization, if you don't have the one in the ring, then it is death on a hot plate. Right, so you really, so it depends on what you're interested in. There are some situations where it's convenient to do that. And people that are interested in looking at these kind of algebraic objects and categorically stuff, sometimes they're the ones that demand that as well. But let me give you a couple of examples. The integers separating real numbers, for sure. This is kind of a first introduction to this. Let me tell you how this is defined. You all worked with this sort of stuff before, whether you were thinking about the fact you were working with it or not. This is called a polynomial ring. You all probably did problems like that, even probably in Calc 2, when you have like Lagrange multipliers, or even in Calc 1, you take derivatives of these various polynomials and so forth. What happens when you add two polynomials with integer coefficients? Bang, new polynomial integer coefficients, right? What happens if you multiply two polynomials with integer coefficients? You never get a coefficient pi, do you? You still get integer coefficients, right? This is actually a good old-fashioned all-American ring, and there it is, right? Can somebody name me some subrings of this? Oh, there's a lot. Zero. There's a subring of that. That's one that doesn't have the identity for sure. Z, 2Z. Here's another subring. Kind of a nifty subring. Here, these are all polynomials whose constant term can be any integer, but all the higher degree coefficients have to be even. It's easy to check that when you add two things in this form, it's still this form. And when you multiply two things in this form, it's still this form, right? So all the coefficients are even except for maybe the constant term can be either odd or even. Right? That's another one. How about this one? You might think of this as all polynomials that have all their odd power terms are at zero coefficients. So you're sort of missing all the odd power, right? That's another example. So subrings galore. Okay. Any questions? Yes.
What's the Cause there's like the two X in front, the. see, bar
This
X.
is just the notation. What this means is, your first coefficient is completely free to be any integer, free to be you and me, but these ones all conform to being even.
So you're not multiplying another X by the.
No, this just symbolizes that all, at the X power and higher, everything is even.
Oh.
Okay, other questions? Subring, yes,
Sorry, is there, like, number of subrings of a ring? Is that like defined for finite rings?
oh, finite rings, yeah, well, even finite rings, good luck with all of that. In fact, let me ask you a simple question. Let's say, gosh, I hope I get this right. How many rings of order 4 are there? I'm gonna have to look this up, but I'm gonna ballpark this, right? It's like 11. Right, so, so even counting the number of rings of order 4 is big, right? And so subrings, that can be very, very complicated. Obviously, for some rings, like if I give you, for example, Z mod PZ, that's a finite ring. The only subrings, counting them very liberally, are Z mod P itself and zero. That's it, right?
Or you try to find
But with
subrings of
other
zero.
rings, it can get much, much more complicated, right? I'm sorry, what?
No, I was saying, where you try to find subrings of zero, that is.
That one would be a doable task. Okay, so a subring of a ring, that is sort of, a subring is to a ring as a subgroup is to a group, no surprise there. But what kind of, back when we were doing groups, what was the kind of special type of subgroup that was like
Normal.
right? Normal were the special ones because they were the kernels of homomorphism, the mod outline, they're very nice. Is there an analog, right? Are all the subrings analogs to normal subgroups, right? Because every subgroup of an abelian group is normal, right? And the answer is when you add the extra multiplicative structure, just an ordinary subring is not going to be quite the animal that we're looking for, right? Subrings are like subgroups, right? What are the special kinds? And these are called in this section, we'll talk about ideals and homomorphisms. And here's where kind of one of the cool things about algebra is we're going to go through a list of homomorphism theorems for rings, just like we did the homomorphism theorem for groups. But guess what? They look almost the same and they're very much in spirit, something that you've seen before, except now we just got a little bit extra structure. So first we begin with the notion of a homomorphism. Definition. Well, maybe RT complaints. And RT function. We say F is a homomorphism of rings if and maybe y'all can help me out here because homomorphisms of groups, what were they? They were functions from one group to the other, but they had respect, man. They respected that structure, right? What do you think we're going to need for homomorphisms here?
It has to be a group of.
Very good, right? A ring, first and foremost, is a group, an abelian group in this case, right? We got to respect that group. Another way that I wrote out, sort of the functional equation that you need. But another way that I could have stated this succinctly is F is a homomorphism of abelian groups. That's all this means. This is exactly the same statement as F is a homomorphism of abelian groups. Okay, but I think we're a little bit incomplete because what sets a ring apart from an abelian group is the fact you can multiply crap, right? We better respect that. So that's what we're going to do. We'll be respecting multiplication. Um, so let me give you some examples. So you should check details on some of these. Okay, no shot there. The identity function from any ring to itself is a homomorphism. Let's let n in natural numbers. Okay. Go to F from C to Z mod n. And our rule is going to be F of K equals K bar. Check this is a ring. Here's another good example of ring that I'm digging on. Actually, I'm gonna call this one P. Can anybody think about a way to do this? But give me a number. That'll work. Because if you look at P of F of X plus G of X, this is F plus G evaluated at 3, which is F of 3 plus G, which is B of X. And F of X times G of X equals F of X, G of X, evaluated at 3, which is F of 3, G of 3, which is P of F of X. P of X. And in fact, hopefully, me calling on a random number gives you the following idea that the 3 didn't matter. It could have been any number. It could have been 0, 27, whatever you think. So let me wrap up with a definition and a remark. Definition. Let P from part of C be a ring homomorphism. And the kernel is X and R such that P of X. This is very much like the null space of linear transformation. And in fact, what it is it's the set of everything that goes to 0. So basically it's the kernel of the group map. Because a homomorphism C is actually a group homomorphism, so it's just everything in the kernel of the group homomorphism. And we're gonna see that this is very important. My last remark is, we've defined homomorphisms, all adjectives apply, right? So if I say a monomorphism, it's a ring homomorphism 1-to-1, a ring isomorphism, even a ring automorphism sometimes. So all those adjectives apply as well. Any questions for next? Oh, yes.
So the normal group, with respect to the, like the kernel is also like the kernel for, like, it's also suffix.
Actually, the kernel is a subring, and more than that, it's an ideal. I haven't defined yet, but we'll talk about that next time. Others? Okay, I will see you folks on